For over 150 years, geologists have been mapping out and describing and interpreting the fantastic structures we see in mountain ranges like the Alps. But what happens to these structures in the subsurface as you go deeper into the earth? It's a question that can be addressed by deep seismic reflection profiling. It's a technology that was developed in the 1970s, particularly in North America. The method involves sending acoustic energy, rather like tiny man-made earthquakes, by bouncing trucks, the vibrosize method. And to get enough energy in, a herd commonly bounce in unison, as a train of vehicles. And the record of reflected energy that is received back at the surface plots up as a seismic profile like this.
As we'll be going back 40 or 50 years, it's worth looking at the seismic images from that time. And I'm going to use some images from this classic atlas put together by Burt Bally. The seismic reflection method has been fully established for imaging sedimentary rocks with the good reflectivity representing different packages of sedimentary layers, and it may even be able to image fault systems or at least deformation structures in the subsurface. So the challenge is we can image sedimentary rocks really well with the seismic reflection method, but how well does it image structures in the continental crust, in the heart of mountain belts? And that was the mission in the United States from about 1975 by ECORS-CROP, the Consortium for Continental Reflection Profiling. And the Bally Atlases contain a really influential project carried out by the ECORS-CROP team in the Southern Appalachians. And this is their remarkable profile through that region, showing a major low-angle structure running beneath the Appalachian mountain belt and fold belt that lies at outcrop. Their interpretation of this structure is as a low-angle thrust detachment that's carried the Valian Ridge and Blue Ridge and internal parts of the Appalachian chain right across the crust of this part of North America. Well, given the success of the ECORS group in the Southern Appalachians, unsurprisingly, other groups wanted to have a go at imaging their mountain belts. Well, let's get back to the Alps.
Well, in the 1980s, a seismic profile was acquired through this landscape. Let's just consider the technical challenges of doing that. Take a train of vibrosize trucks, easy on the flatlands of, say, Utah. But this is the Alps. Beautiful Beaufortain. The route for the vibrosize trucks lies on windy mountain roads, first climbing up through the forests and up to the high pastures. In 2025, the road was used as a stage on the Tour de France. It's not uncommon for the Tour to pass this way, climbing up through this landscape and swooping down the far side. Though of course professional cyclists are much faster than seismic trucks. So this is the Cormet de Roseland, a pass rising to just under 2 kilometers above sea level. And the profiling continued through the Vanoise there, those snow-coloured hills in the distance, and connected up with the profile acquired on the Italian side. Dramatic landscapes and challenging terrain for acquiring seismic imagery. But what geology and tectonic structures are to be found along the transect?
So let's use this map sheet from the structural model of Italy to locate where we're talking about. This is the main Alpine arc sweeping around from Austria right round to France, and we're dealing with the Western Alps. So let's just fold this map up and just deal with the segment we're interested in today.
So I've created a scene about 260 kilometres across. And let's do a quick geo tour across it, starting over in the northwest corner. We're looking out across the Alpine foothills and the rolling hills of the Jura, uplifted ridges of Jurassic and some Cretaceous limestones, with strips of preserved tertiary detritus, molasse, lying in the valley bottoms. It's one of the world's great fold and thrust belts.
So that's the Jura fold belt. Those rather wonderfully named range of ridges over there are the Boogie Hills. So southeast of the Jura fold belt, there's the remnants of the fallen basin, covered with a little bit of cloud cover down there. But then coming further, we're going into the subalpine chains.
So, on the map, the Jura fold belt and vestigial remnants of the fallen basin. Switching our view to the subalpine chains.
So the subalpine chains, significantly higher topography than the Jura, and are also more structurally complex.
Let's build a simple cross-section using the surface geology. The Jura fold belt in the Boogie Hills, the remnant fallen basin of Annecy, passing east-southeast into the more complex structures of the subalps.
And then continuing our story further southeast, in the distance there, Mont Blanc, uplifted crystalline basement, continental crust, the external basement massifs.
From our viewpoint, over 70 kilometres to Mont Blanc. Here it is on the map. So let's get a bit closer into the Alps. A new viewpoint. Those hills, the Chaîne des Aravis, are the backside, the eastern side of the subalps, and they continue south into the misty distance. But we're now seeing on to more elevated rocks, uplifted continental crust.
So, as we go further into the Alps, the elevation increases, those snowy hills, and those are elevated basement rocks, so pre-Triassic rocks brought up to the surface, and these are the so-called external basement massifs.
Let's just add the massifs onto our section.
And then in the back, those snowy hills, which are the internal part of the Alps, so designated because they're much more highly deformed, and you go into strongly metamorphosed rocks right in the far distance, where the sun's still picking out the snowy peaks.
So these are the so-called external zones of the Alps, with the more complex metamorphic interior further east. And the boundary between the internal and external Alps is the frontal Pennine thrust, and more about that later.
So the seismic profile started way out on the orogenic foreland and passed through these areas here, the subalpine chains. But really their target wasn't to image the structure of those sedimentary rocks, but the deeper structure that passes down beneath here and on into the middle part of the Alps.
This is the line of the Alp 1 profile of the French seismic program ECORS, and the profile was continued by their Italian counterparts on the CROP project. Their mission: to see how alpine structure of the mountains passed into the crust below.
So in the years preceding the acquisition of the seismic reflection profile through here, there was other seismology, a seismic refraction profile, a wide angle experiment. So what did that find?
The Moho on the northwest side, that's the base of the European crust, and it can be traced under the Alps, showing thicker crust beneath the higher mountains, as expected. But the experiment didn't reveal its continuation further east. Meanwhile, seismology on the Italian side revealed an elevated Moho uplifted mantle, the so-called Ivrea body. Did these join up? And if so, how?
So the wide angle experiment is giving us good information about the position of the Moho under the Alps, as well as the seismic velocity structure. But it's not giving us information about the position of any shear zones or any detailed structure associated with the thickening up of the crust. That's where the seismic reflection profile comes in. So I guess it's time to have a look at that.
Crustal reflection imagery is hard to interpret directly. So back in the day, geophysicists made line drawings of the more prominent continuous reflectors. And this is what the ECORS team published in 1987, as tarted up a bit by Robin Marchand of Lausanne. And we can add those mohos. So now let's look at some structures. Can we see through the fog? Starting with the frontal structures. Is the Alps as thin-skinned as Cocourt revealed for the Appalachians? Well, let's get back to the Jura and Subalps. Commercial seismic profiles had long revealed that the Jura were underlain by a panel of continental crust, with thrust detachment. But did this thin-skinned explanation work beneath the external basement massifs? Restoring cross-sections suggested that it did, at least a little way. And on the seismic, maybe it does. But there's no sign of an Appalachian-style detachment continuing on beneath the internal Alps. Mind you, they on the other hand are dominated by extensive subhorizontal reflections. They're really prominent. But the structure of this area of the Alps at outcrop is really complicated. So what is this reflectivity actually imaging? It's a bit of a puzzle. So let's go to a structure that ties more clearly to surface geology. The frontal Pennine thrust, the tectonic boundary between the internal and external Alps. So, let's get back to the field.
Well, the profile went past some pretty big landscape. That's Mont Blanc. But it also went past some pretty big structures. Let's take a look.
The thrust is really straightforward to map through the outcrop in this landscape. And we can see it on the ECORS Alp 1 seismic profile.
Well, an individual thrust plane is unlikely to have sufficient acoustic impedance contrasts across it to generate significant reflectivity. But there's more going on than just the thrust plane here. So those benches on the hillside opposite are formed by turbidites, the so-called Flysch de Tarentaise. If you're in Switzerland, you call it the Valais zone. Deep water sandstones, apparently simple, they're really deformed, but they're dipping down into the valley beyond, down towards the east. A whole package of layered strata. And if we nip back down to the road section along which the profile was actually acquired, we can find another component to the geology there that may also have generated reflections. So the frontal penine thrust zone has Jurassic strata in its footwall, including those rocks over there, which are limestones, and they're repeated on a series of thrusts. So a tectonic layering in here that will for sure enhance the reflectivity of the frontal penine thrust zone. So let's just sit down and have a look at how that thrust zone is imaged on the ECORS-CROP data.
This is the thesis of Guy Sénéchal from the early 1990s, and he reprocessed the ECORS profile.
So I've got a copy here of the ECORS profile, ECORS Alp 1, and there's some really prominent reflectivity coming down from the Cornet de Rosan, the pass up there, and you could trace it all the way down. So let's just interpret that up.
These reflectors could represent the layered sedimentary rocks either side of the frontal penine thrust and down through the upper crust of the Alps to around 5 seconds two-way time, equivalent to around 14 kilometres depth. So here we can trace a structure from outcrop at least through the upper part of the alpine crust. But of course there's more in this image than just the frontal penine thrust zone, though it's difficult to relate these to actual structures, certainly for the reflective uppermost crust under the internal Alps.
Well, it's always good to put the seismic imagery in front of the outcrop.
For the frontal penine thrust, we can at least relate what's at the surface to deeper in the crust of the Alps. But what about other structures nearby? Into the external basement massifs just west of the frontal penine thrust. We can check out how these rocks are imaged in the ECORS seismics. And the answer is, it all looks transparent. Does that mean that the rock has no structure? This is a bunch of basement called the internal Belladon Massif. And in this ground there's plenty going on, intense deformation fabrics, though it's not clear how much relates to alpine mountain building and how much was inherited from ancient pre-Mesozoic tectonics. There's a lot of it, all stood on end.
So the challenge is with these really steep fabrics that if the seismic ray paths are coming in like this, they're going to be reflected deeper into the earth, not returned up to the receivers. So you just won't image this stuff. We won't see this structure on the seismic profile.
It's a key point. Seismic reflection profiling is designed to image structures in particular orientations, essentially gently dipping or flat lying. We won't be seeing everything.
Well, the internal Belladon Massif isn't just crystalline basement. There's also another component to the geology. And if you look over on the far hillside there, there's an orange gully. Well, that's a slice of Triassic rocks, sedimentary rocks caught up in the basement. And there are various ways in which people have proposed that's happened. But from a seismic imaging point of view, it really doesn't matter, because just like the fabrics we've seen in the basement, the slices of trias are also really steep, which means they're just not going to get imaged.
So finally, we should address the key challenge for deep reflection profiling: imaging the deep crustal structure. What underpins the high mountains? Can we see through the fog? We can simplify the question. It's about how the European moho and the frontal penine thrust relate to each other. Traditionally, it might be interpreted like this, and I've got an angle on this from very early in my career.
Well, the ECORS profile went straight through an area that I worked on for my PhD a year or two before the seismic line was acquired. And on the basis of my fieldwork there and the sections that I constructed, I'd made some predictions about the deep structure of the Alps along this transect. So I was pretty excited when the deep seismic reflection profile was acquired.
As part of my PhD, I used an estimate of the amount of displacement on structures I'd mapped to outcrop and restored this, assuming an initial crustal thickness based on sedimentary rocks that once lay on top. This is crustal balancing. This is a version I drew up slightly later that pushed the idea into the internal Alps. And to make it work, the crust of the external Alps must underlie the internal zones, and so the frontal penine thrust had to remain in the middle crust and not dive steeply down to the moho.
So I guess the question is, how well did my interpretation stack up against the imagery acquired from the seismic experiment? Well, not bad, because I'd forecast a panel of crust of the external Alps continuing beneath the internal Alps. Therefore, the frontal penine thrust should be a relatively low angle structure passing deep down towards the east. And that's indeed what the ECORS-CROP profile showed.
Or at least seems to. But the crust that once underpinned the internal zones of the Alps is missing and presumably has been subducted beneath northern Italy. Although these days I'd probably have this crust originally significantly thinner, although even here it's been thinned by a factor of 2. But thinner crust could mean that the frontal penine thrust is a bit, but only a bit, deeper than I suggested back in the day.
So it's always good to get some geophysical data confirming your structural interpretations.
Namely, that European crust has been taken down and subducted beneath northern Italy. This proposition should have been testable by referring to images acquired by the Italian CROP programme. But at the appropriate depths, the image quality is terrible, so no tests are available here. Maybe this isn't surprising. As I pointed out back in the day, the subducted crust will be at eclogite metamorphic grade and have new seismic properties that will make it difficult to tell apart from the upper mantle. But anyway, the seismic experiment wasn't optimised by the CROP team to test this interpretation, so I'll have to leave it hanging. However, the ECORS-CROP experiment has generated results in imaging the frontal penine thrust. But overall, this is a biased image, emphasising gently dipping shear zones and structures and neglecting steeper fabrics. So this is only a partial view of mountain building processes and their deep structure. The challenge of testing crustal scale interpretations for the Alps remain largely unmet.
So that's been a look at how deep reflection seismic profiling has revealed something of the crustal structure beneath the Alps. Well, over the years there have been many interpretations published of the ECORS-CROP line, and indeed there have been other deep seismic reflection profiling campaigns, particularly in Switzerland. But it has to be said that the quality of the imagery for all this effort is pretty poor. The seismic method is not great at revealing crust or structure. It's great in sedimentary basins, where you can use the sedimentary layers and their fault systems and infer deeper structure from those. But in mountain belts, actually, it has to be said that the deep seismic reflection profiling method has been, overall, rather disappointing. But what it has done is inspired a whole bunch of research into the tectonic evolution of mountain belts, and that has been a good thing.